My alarm was set for 6:30 this morning. I woke up and began my day. I was ready for my presentation 1 hour before, and I noticed that you've all arrived here on time. The consequences of you being late were not serious. Mine, on the other hand, were. So we adjusted our arrival times accordingly. We have absolute certainty on the time and absolute faith in the devices that we have for measuring time. If I had to distill my research down into one word, it would be certainty. And the key design concept that I need to put across today is that in situations where we are more certain, we can naturally adjust the factor of safety to increase design efficiency whilst keeping in mind the risk, in exactly the same way as we all did to arrive here on time this morning. And this concept is enshrined in the Eurocodes and is referred to as reliability analysis. Structural health monitoring, SHM, is the practice of putting sensors on structures to understand their behaviour, and my research deals specifically with the measurement of dead load. Dead load is the weight of all the permanent elements, as opposed to the live or the imposed loads, which are the people or furniture within a building. I've not included live or wind loading in my research, but this approach can be similarly applied. And there's been work done already applied to the strength of reinforcing steel based on laboratory test results. SHM in practice is usually used to check everything's okay. My argument is SHM can be used to increase certainty in the same way that watches have improved our timeliness to enable us to design structures more efficiently. This research is crucial because we all live in a world of finite and diminishing resources, and the world's rapidly growing and urbanising population needs to be housed and to work in buildings. These buildings are currently responsible for 39% of global carbon emissions. This issue is especially important to the developing world, where the rapidly expanding total building floor plate area dwarfs the relatively minor increases in the United Kingdom. Efficiently designed buildings utilise less material and spend less carbon, and vice versa. Typically within a building, it is the structural elements that have the largest embodied carbon footprint. My research question is, can SHM enable structural design efficiency, and how can this be achieved? Of this list of embodied carbon mitigation strategies identified in the literature, this research deals with better design, refurbishment of existing buildings, and extending the building's life. The natural tendency of designers to over-design is called habitual over-design, and this has been estimated to cost approximately $1 billion per year in structures alone. Over-design is expensive and bad for the environment, but it creates a surplus building capacity that is not currently utilised. Building expansions are not uncommon, and the South Bank Tower expansion was a prime example of where surplus capacity was used to add 11 more stories to the tower and generated a huge carbon saving when compared to demolishing and rebuilding the tower. The SHM dataset that I've used for this research was collected from Soho Place Building B, which is a 10-storey statically indeterminate steel frame structure built on top of Tottenham Court Underground Station. This was a limited study done on one building. The columns landed on elastomeric vibration isolation bearings to prevent the vibrations from the underground travelling up into the structure. 48 out of 56 of the bearings were monitored. As the structure was built, the displacement of the bearings was measured, and the load from each column was calculated using the stiffness of the bearings. I compared the measured loads with the predictions made by the structural engineer who were on this project. The total load measured was within 9% of the predicted, which I think was a good result. These were the preliminary results from the 3 most heavily loaded columns that I used to validate this approach. You can see as the building is constructed, the lines with the circle markers representing the measured values matched quite well to the predicted values shown by the thicker lines, and the colour is consistent for each column. Reliability analysis is represented by these 2 probability distributions. The yellow curve on the left represents the load with the mean at its peak. Think feathers on the left and dumbbells on the right. And the black curve on the right is the building resistance, or the strength, again with the mean at its peak. Think Mr. Skinny on the left and Arnie on the right. The design codes tell us the mean load and the factors of safety to use, which set the distance between these 2 curves. Then we size the structural elements so the strength of the building can safely carry those loads. If these two curves are spread wide apart as shown, it's like Arnie lifting a feather. The probability of failure is very low, but the carbon spend and building cost are both excessive. If the curves are too close and the peaks coincide like this, it represents a factor of safety of 1 and is the definition of structural failure. The method for reliability analysis is set out in Eurocode 0 Annex C, and it's summarised by this equation, which is the factor of safety is equal to 1 plus alpha times beta times standard deviation. Alpha is the form factor and is nominated as 0.7 in the code, and beta is the reliability index and is nominated as 3.8. To calculate the design load, we multiply the mean dead load by this widely used factor of 1.35 and add it to the similarly factored live load. The standard deviation is our degree of certainty, and you can see by this equation, if our degree of certainty was 100% like we have in our watches, then the standard deviation would be 0 and the factor of safety would revert to 1. And this is the crux of reliability analysis. This is shown graphically here, and you can see how the shapes of the curve change based on the different degrees of certainty. The low and wide yellow curve represents the assumed certainty in the Eurocodes. But on this building, we have an SHM system for accurately measuring the load. So our degree of certainty has increased. And this can be seen by the shape of the green curve, very skinny with the tails of the curve close to the mean at the peak. The mean load has not changed, but our certainty of the load has increased in the same way that we are all sure about the time. Now look at the required design resistance showed by the black line. It shifts to the left to reflect the higher degree of certainty shown in the green, meaning smaller structural elements, less cost and less carbon. We targeted a standard deviation of about 0.02, so the factor of safety reduced from 1.35 down to 1.05. This is a difference of 0.3, which generated a surplus capacity of 30% of the dead load, which could be used for future building expansions. Okay, so this is what actually happened. This is the probability distribution of the factor of safety. And again, the yellow curve represents the nominated Eurocode position and is much skinnier, so is more certain than the black line representing what we actually measured. Unfortunately, what this is saying is that there is a lot less certainty in the results. And based on this distribution, the factor of safety actually increased from 1.35 to 2.27. But we don't need to choose either or. We can use Bayesian updating to combine these distributions. And that's what I'll be doing over the coming months. I believe the main reason for this uncertainty is that our current mathematical models cannot accurately predict the load paths in statically indeterminate structures. This is most likely due to construction build sequences, and the connection and the bearing stiffnesses behavior in the models are actually different in reality. We need to get better at this. We need to do more monitoring with back analysis, and engineers need to get better at applying statistics. I can see a two-phased implementation of this approach. Phase 1, more SHM to improve our monitoring and our modelling, and then also applied to live and wind loading. And then the work already done on resistance should be extended to concrete and structural steel. Phase 2, reduced partial factors could be implemented as part of the initial design for similar buildings with consistent client, designer, builder teams. If we do this, then as buildings become more slender, serviceability design will become the critical design load case, and a similar approach can be applied. I encourage all designers to try a reliability approach on paper to an existing building to see what potential cost and carbon savings are. Thank you. Thanks, Cam.
Thank you very much, Ben. So now I open the floor to any questions. Again, if you'd like to send them in, and I've got a number coming in, you'll be pleased to know, Ben. Let's start off one directing question from William Charlesworth, who has just asked whether you're actually stating that the columns in your chosen project, the Sorrel Place, are, in your view, actually overloaded. Is this really the case?
Okay, so what I've been looking at here are predicted loads, and I've never actually seen what the design loads are because Arup haven't given me that information. But when I did look at the overloaded columns with the low factors of safety, when I looked at the neighbouring columns, they had a very high factor of safety. So it looks like the building distributes the load in a way that's safe. So yeah, I think I don't think the columns are overloaded, but they might be marginally, but the columns next door can carry the load, in short.
Okay, thank you for that. We have another question here that's come in. Given the possible unknown unknowns involved in construction and design, and the fact that materials can be highly variable, how far do you think we can go in reducing factors of safety? Because that's what I think you're actually inferring.
Okay, so there's always two curves to look at, one being the load and one being the resistance. And it's my personal belief that we need to be collecting more data and use, instead of just guessing what we think the factors of safety should be, actually measuring and calculating what we're doing. And I think if we understand better about the strength and about the loads, we'll be able to get a better idea of what the factors of safety need to be. Sorry, I'm just having a few problems with my with my Zoom here, Cam.
That's okay. Well, look,
yeah.
Let me go on to another question, and this is actually one from me. There's been an enormous amount of work on the strength side of things, the calculation of material strength, measurement strength of steel, strength of concrete and all that. But as you suggested, the loading can be highly variable. How much did you find in your research was actually out there in the way of evidence of the variability and measurement of actual loads applied to the buildings or the different areas you looked at?
I've been searching my whole career for buildings where load has been measured, and I've managed to find 3. So the first being Condor Towers in Perth, which I had some involvement in, and that is what sparked my passion about monitoring and about research in this area, because when we looked at the monitoring from that building, the thermal distortions of the building applied loads to the columns and the piles that was bigger than any design load. And so that, for me, just indicated that the way we design for load needs to be looked at. But we seem to just take what's in the code as face value, even though we have these systems of measurement which will drastically improve our understanding of our loads and our mathematical models. I mean, fundamentally, what I'm trying to do here is take the observational method used in geotechnics to improve design efficiency and apply it to the structure. But unlike geotechnics, we can't change the structure as we're building. So initially, I want to calculate the surplus capacity and give it back to the owner so that it can be used for future building expansions. And at the same time, that will enable us to improve our understanding of structural modelling so we can apply it to all structures. Does that answer that question?
Yeah, one more quick question. Did you, in your literature review, look into how factors of safety were being implemented in other industries, say aerospace or automotive industry, and compared to our industry?
I did, and I think we have some good learning, especially from the aeronautics industry, where what they do is they look at critical component failure. So they look at the component that's going to cause the plane to crash, and they make sure that's got a high factor of safety on it. But then where you've got a component which is non-critical, they reduce the factor of safety. And really what the reason for that is because when a plane has a much higher weight penalty than does
That's 15 minutes.
Than does a building. So they're incentivized to go for these gains. And I think, yeah, I think I agree with your sentiment, Cam. We should also be doing that in construction. I mean, choose which elements we're going to allow a reduced factor of safety on specific in each building.